Yes, ma'am.
So if you see this, just a second. You can see this figure, right?
Yes, ma'am.
Okay, so this is a circle. The circle represents the area just below the lamp, how the light will be distributed in the horizontal plane. Okay, so this 0 means just below the lamp. Then if you move in the anti-clockwise direction, so it will be 0, 15, 30, 45, 60, 90. Above the lamp, it's 180. Then 270, then again 360 means just below the lamp. So how the light will be distributed around the lamp in the horizontal plane from the down hemisphere to the upper hemisphere. So this is the total light emitted by the source, how the light will be distributed around the lamp. So the total light will be distributed in this way. So you can see these values like minus 20, minus 10, 0, 10, 20. So this different, there you can see 4 circles, right? So the circles indicate different intensity values. Okay, the total area under this blue line, this is the total light, total luminous flux. But how to means how the light will be distributed depending upon the luminous intensity. মানে কোন দিকে বেশি লাইট যাবে, কোন দিকে কম লাইট যাবে, that parameter is the luminous intensity. So if you see, the maximum light will be distributed at 75 degree, and that value is like almost 10 candela. Just below the lamp, there will be no light. Around 90 degree, we will have 10 candela. Then around 165, we will have some 2 or 3 candela like that. So these values, it represent different luminous intensity.
Okay, ma'am.
Okay.
I thought it was luminous flux. Thank you, ma'am.
No, it's luminous intensity.
Okay, ma'am.
Okay. For example, suppose a cricket field, the light will be focused towards the pitch, so that the maximum light reaches towards the pitch area, not the entire field, right? Accordingly, the rest amount of light will be distributed in the rest of the field. Okay, like where our application area is located, the light will be focused towards that part. Maximum intensity will be towards that application area. Okay. Okay, so I want to show you a few examples which are covered in the previous discussion. এগুলো তোমাদের এক্সামে থাকে, like if you see this question, 200 watt filament lamp is suspended from ceiling. This is the mounting height, this is the working plane diameter. Then you have to find the average illuminance and illuminance at center at periphery. So normally এগুলো আমি ক্লাসে করাই, but it's not possible now to compute this in the online class. I hope you will practice this in your home, or if you have any question, you can ask me. You can take a picture of this. So to solve this problem, we have to use the Lambert's cosine law, right? There is a circular table. The filament is suspended. It's the mounting height is like 2.8 meter. So you have to find the illuminance at the center as well as at the periphery, and what will be the average illuminance. So at the center means just below the lamp. So you will be I by d square. What's the value of I? I is not given here, but you can see the wattage and the efficacy is given. So from there, if you multiply this, you will get the total amount of lumen. Then total lumen we know. So around the sphere, it will be this lumen per key. Lumen per key hobe unit. If you want to calculate candela, it will be the unit lumen per what? Luminous flux per solid angle, right? I mean, if the lamp wattage is 200 watt, the lamp efficacy is 15 lumen per watt. Can you tell me what will be the mean spherical candle power? what will be the intensity if it distributes the light symmetrically around the lamp? Well, what will be that mean candela value? Wattage is given, efficiency or efficacy means lumen per watt is given. So what will be the total lumen output of this filament lamp?
200 into 15.
Yes, it's 200 into 15, so 3000 lumen. So luminous flux or the total light output from the lamp is 3000 lumen. So now what will be the luminous intensity? Luminous intensity is luminous flux per unit solid angle. So if the profile is like a sphere, so the solid angle of a sphere, it will be কি হবে যদি একটা sphere হয়, yes, it's 4 pi r. We know that the solid angle for the entire sphere, it will be omega is a by r square. For a sphere, it's 4 pi r square. So for the full sphere, it's 4 pi steradian. So the mean candle power will be this 3000 lumen by 4 pi. So that is my intensity, I. Now, if you want to calculate the illuminance at center, that will be I by d square. So I by the height of the this 2 meter, that is the mounting height of the filament lamp. Then at the periphery, so then you have to use I cos theta by d square. Okay. For this question, a luminaire is suspended above the center of a circular table of 3 meter diameter. The luminaire mounting height is 1.8 meter. Intensity distribution is given here, which is I theta is 2200 cos theta. You have to find the illuminance at center at periphery. So again, I by d square or I cos theta by d square. So I theta is given, means what will be the value of the intensity at any particular angle. So when I is 0, is just below the lamp, it will be 200 candela. When I theta is 90 degree, so it will be 0. Okay. So accordingly, you have to find the illuminance at those points. This is another one. This is from the radiation law. The discharge lamp has 4 lines at this wavelengths. These are the radiant power density. Corresponding V lambda values are given. So you have to find the total lumen output. Okay. So I'll send you these problems. You can solve, and if you have any question, then you can ask. Okay, so our next topic is photometry. Photometry is, as I told, is the measurement of those lighting parameters. Means how to measure the luminous flux, luminous intensity, illuminance, etc. So this is required to quantify the light and those lighting parameters. So to measure the light level, there are 2 methods. One is visual photometry, another is physical photometry. So visual photometry is observer based, means it depends on the detector or the human eye. The human eye is the detector here. This is the observer based photometry, and detector based. Detector means here we will use a physical sensor, and the response of the sensor will be equal to the human eye. Okay. So the visual photometry is not that much reliable because it totally depends on the perception of the observer. So from person to person, the result may vary. But in case of physical photometry, our sensor is standardized. The response of the sensor is like the V lambda curve or the V dash lambda curve. So we will get more accurate result in case of the detector based photometry. So in all the instrument, it's physical photometry. So photometry deals with the measurement of visible part, which is 380 to 780, and for the entire optical radiation range, it is called as radiometry. So if my sensor can detect from UV to IR, like from 100 nanometer to 1 mm wavelength, then that is called radiometry. Otherwise, it is photometry. So the photometric detector, it must have the spectral response identical with the CI standard observer, that is the V lambda or V dash lambda curve, and it must have wavelength non-selective response. So we'll see this. That means, what is CI standard photometric observer? We know that there is one V lambda curve for photopic vision, or one is V dash lambda for scotopic vision. Okay. So this is the normalized V lambda and V dash lambda curve. Okay. So this is just different radiometric and photometric parameters. All these measurements are not in your syllabus. Just for your information, we know that wavelength, the unit is nanometer. We can use spectrometer. For color, there is spectrophotometer or colorimeter. You know about the constant deviation spectrometer. So like there is spectrophotometer and colorimeter, which can measure the color depending upon their respective wavelengths. Energy, we can measure using radiometer. Color temperature or CCT, probably you have seen that meter, right? For measuring the CCT. Then for luminous intensity distribution, we have goniopotometer. For luminance, we have luminance meter. For SPD, we have spectroradiometer. Power consumption, wattmeter. Voltmeter, ammeter, we know this is the electrical parameter. Then lumen output, we can use intrigating sphere or goniopotometer or goniometer or photometer. Lumen distribution, again goniopotometer. Illuminance, this is called Lux meter and luminance meter. Then these are other properties of the materials like reflectance, transmittance, etc. So these are the meters. Now here you can see few are written as laboratory and few can be measured in the field. Like if you want to measure the color of any source, so of course we have to measure that color in the lab only, because if we do the measurement in the outdoor, the color of the sunlight during daytime or any artificial light during night time will be mixed, right? So to get the accurate result, we have to do the measurement in a dark room. Why dark room? Just to avoid any kind of reflection from the other properties. So to get the accurate color of that source, we have to do the experiment in the black laboratory. Then energy. Energy, you can, of course, you can do the measurement in field. Like that. Another one is, okay, this one is laboratory or field. So if you want to measure the light level of any room, of course, you have to do the measurement in that room. If you want to do the measurement of any street lighting, you have to do the measurement on the street itself. So that's why you have to do the measurement either on lab or field, like that. Okay. So here we have Lux meter for illuminance. You can hear me, right?
Yes, ma'am.
Okay. So here we have Lux meter in your syllabus to measure illuminance. Luminance meter, this is also important, but you have Lux meter in your syllabus, Intriguating Sphere, this goniopotometer, that's it. So these are the important parameters which we need, like Lux meter for illuminance, luminance meter for luminance, this is Intriguating Sphere for luminous flux, this goniopotometer, bench photometer for luminous intensity, chromometer for CCT, and spectroradiometer for the SPD. So among these, you have seen the spectrometer and chromometer, right? So the basic instrument is the illuminance meter or Lux meter. So the actual name is illuminance meter because it can measure the illuminance. Now you know the unit of illuminance is lux, so widely it is called Lux meter. But to be correct, the name is illuminance meter. The feet candela is not used that much, so that's why it is called Lux meter. So Lux meter can be used to measure the illuminance of any point, right? So right now, if you want to measure the light level on your work surface on your table or wherever you are, you have to put the lux meter on your table. So it can measure the received light on that surface. So how to measure that lux meter? For that we need one sensor which will detect the light, and the response of that sensor will be equivalent to our human eye. মানে আমি চোখ দিয়ে যতটা দেখছি, the sensor will see that same amount of light level. Okay, so here this white part, which is the light sensitive part or the detector. So it is used to measure point specific illuminance. Why point specific? Because on your entire workspace the light level may be different of the different points of the table, right? So if you want to measure the illuminance for any point or a very small area, then we have to put the illuminance on that point only. Then if you measure for all the points, then you can do the average illuminance. So it use measure point specific illuminance on any plane of orientation. Okay, like if you want to measure the vertical illuminance, so if you see any wall, so the wall, it will be like vertical illuminance, not the horizontal illuminance, right? So then you have to place the lux meter on the wall. So then the sensor will measure the light received on that wall. So either it may be on the horizontal plane or in the vertical plane. You have to place the sensor accordingly. So this is used to measure point specific illuminance. Okay, so we can do the measurement both in indoor or outdoor. So it consists of a photocell, and which is calibrated in lux or feet candela, by which we can take the illuminance reading. So the photocell, it consists of a metal plane coated with a semiconductor which is exposed in light. The electrons are liberated from the metal surface and are trapped at the interface unless an external circuit is provided. Like I think you heard about LDR, right? Light dependent resistor. You know LDR? কেউ শোনোনি LDR? ইলেকট্রনিক্সে বা কোথাও ফার্স্ট ইয়ার সেকেন্ড ইয়ারে?
না ম্যাম, শুনিনি।
আচ্ছা, এলডিআর হচ্ছে
হ্যাঁ ম্যাম, আমাদের প্রজেক্ট ছিল।
কিসের প্রজেক্টে?
স্কুলে।
আচ্ছা, LDR is, this is a resistor. The resistor is light sensitive, means the maximum resistance will be in complete dark condition. It will exhibit maximum resistance in during dark, means when there is zero light, zero lux, and the minimum resistance will be in bright light, মানে যেরকম property হবে accordingly. So that means the resistance will decrease with the increasing light level. So this is also a photosensitive material, right? Now if I want to make this lux meter sensor, so I have to put a filter which is equal to the V lambda curve, right? This is a photosensitive material. Similarly, we have another photosensitive material at this detector part. Okay, so the detector part will receive the light. Accordingly, some electrical signal will be generated. It may be in form of voltage or current, whatever you need to convert it to the lux level. That means whenever the photocell receives the light, when it is exposed to light, the electrons are liberated from the metal surface, which are trapped at the interface. And then if you connect it to the external circuit, there will be some amount of current. So then you have to calibrate that in the illuminance, either in lux or feet candela, whichever is required. So in the instrument, this photocell is a selenium cell, but nowadays all the silicon cells are used, because silicon cell response to অনেকটা equivalent to the V lambda. So আমাদের filterটা will be, I mean the use of the filter will be easier for the silicon cells. So nowadays all the sensors are mostly made of the silicon cell, this part. Okay, so these are the basic features of a lux meter sensor. So can I use a LDR as a lux meter sensor? The answer is no, because this light sensitive material, it must show these three properties. One is linearity of response, one is V lambda correction, another is cosine correction. So what is linearity of response? Linearity of response means the response of the sensor will be linear. what is linear? We know that illuminance is luminous flux per area, right? So E is proportional to luminous flux. So for accurate measurement, the response should strictly proportional to the luminous flux falling on the cell over the range which the instrument is intended to measure. And linearity depends on the resistance of the external circuit, which should be as low as possible. So phi by A, this is my illuminance E, right? So this E will be proportional to the luminous flux. The response must be proportional, linear. So যদি কোনো photosensitive material এর response এরকম linear হয় যে phi যেরকম change হবে accordingly the illuminance will also change, so then that it will satisfy the one criteria that the response is linear. The second criteria is color correction or V lambda correction. Now what is that? So the photoelectric cell is a device which responds to a radiation at least partly in the visible spectrum. So this dotted line, this is the suppose response of any material. So this response must be equivalent to the V lambda curves, so that we can replace our eye by this detector. মানে আমাদের চোখ দিয়ে যেরকম দেখবে আমরা ডিটেক্টর দিয়ে সেম দেখবো. So for the measurement of light, the cell response require correction so that it will have same form as the CI V lambda curve. So that's why a filter called color correction filter or V lambda correction filter is placed over the cell. So we have the raw material which is showing the linear property. Then we have to put a filter over that material which will correct the response same as the V lambda function. Okay. এবার এই দুটো যত অ্যাকিউরেট হবে, means this CI curve and the response curve যত accurate হবে, accordingly we will get more accurate result. For example, we have Lux meter of 5,000 rupees in our lab, and we also have like more than 1 lakh rupees in our lab. So of course you can understand the accuracy of the 5,000 rupees Lux meter and the 1 lakh rupees Lux meter. Okay. Then the cosine correction. The illuminance varies as the cosine of the angle of incidence of the light. So if you remember the Lambert's cosine law, the I is I max cos theta. I theta is I max cos theta. Illuminance at any angle, this will be I max cos theta. So illuminance measured with a bare photocell falls away faster than this because its surface reflects an increasingly higher proportion of the incident light as the angle of incidence increase. The profile of the photocell must be sphere. A specially designed translucent diffusing disc or dome of diffusing material is placed over the photocell. This is provided for cosine correction. So can you see this dome? These are some flat surface, right? So the material which are using, that is flat surface, but just to make it a sphere profile here, can you see this dome? Is the picture is visible or flat লাগছে? এটা কিন্তু flat নয়, বুঝতে পারছো ফিগারটাতে?
Yes ma'am, বোঝা যাচ্ছে।
হ্যাঁ, বোঝা যাচ্ছে না? এই প্রোফাইলটা এরকম করা হয় just to make it so that it follows the Lambert's cosine law. We know that the profile of this Lambert's cosine law, if any material follows this, the profile will be like a sphere. So that's why this cosine correction filter is placed over the V lambda correction filter. So at first there is the material. The material will be light responsive, light sensitive. The response will be linear. Then we have to place one V lambda correction over that just to make it same as the human eye. Then we have to put up this cosine correction filter. Why cosine correction filter? So that I theta will be I max cos theta. It will follow the Lambert's cosine law. Okay. So any Lux meter sensor will follow these three properties: the linearity of response, the color correction filter or V lambda correction filter, and the cosine correction filter. Okay. So this is an example. If you have seen the chromometer at our lab, this farm line, this is the response of the chromometer. The dotted line, this is for the CIU V lambda curve. So these are almost same. That means we have replaced our I by this CL200A chromometer sensor. Okay. So this is the cosine correction filter. This is the V lambda correction filter of the CL200A chromometer. This is a cosine correction filter of CL200A chromometer. The price is more than 1.5 lakh of this Lux meter. Okay. So this is, you can see the dotted line here as well as the farm line, almost same. So this is the ideal one. This is the chromometer response. So we have the cell here. Over that we have the V lambda correction filter. Then we have the cosine correction filter. So this is just an example. The specification of a Lux meter. The model is CL200A. These are the class requirement. Class means depending upon the accuracy of the meter. These are some standard. So it closely matches CI standard observer X lambda, Y lambda, Z lambda. There is a CI curve which defines the different color properties. So X, Y, Z, those are those color coordinates. Okay. Just to show you. This is a figure. How do you quantify color? If you see the color properties of your laptop, your computer, you will see the same thing. This is X, Y, Z, three coordinates are there, and this is mixing of RGB. You can see red, green, and blue. So at the center, it has white color because at the center, all are like 0.3, 0.3, 0.3. So at the center you have the white. Then if you move towards the red, you will get like yellow. If you move towards the blue, you will get cyan, violet. Accordingly, all the colors. So to quantify any colors, we use these coordinates X, Y, and Z. Okay. You can see different colors for like yellow is green. So the yellow is green have some specific coordinates. If you want to quantify the pink, we have this coordinates like that. If you want to quantify purple, you have this part. Okay. So at the center, RGB equals, we have white. This part is green, yellow is green. Like whenever you use paint or any editing of any photos, we use different colors, no? So this is that color coordinate, CI chromaticity diagram. And the photoreceptor is silicon photocell. The cosine response within 3% mismatch. This is again those coordinates values, X, Y, Z. Okay. Any question up to this? Anyone? So this is the basic one, which is the Lux meter sensor. Now, any other type of instrument, like for all the instrument, we have the sensor, because other than the sensor, we cannot measure the light. So whatever be the instrument, we always have that sensor present. Any question, anyone? Okay, so then the next one, which is measurement of luminous flux. So luminous flux, this is the total light output or the total amount of visible radiated power, right? Luminous flux or lumen. So the instrument which is used to measure the total amount of light output from any source, that is called Intriguating Sphere. So this is a large Intriguating Sphere. If you have seen this instrument in our lab, I don't know, the lamp is placed at the center of the sphere, then it is closed, then we can do the measurement that what will be the total light inside the sphere. So there are two methods of measuring the luminous flux. One is direct method, another is indirect method. So what is direct method? Here we do the calculation of luminous flux from luminous intensity multiplied by goniopotometer. Like if you see this, if you want to measure, so we have measured the illuminance on this surface by placing over the sensor over this table or whatever it is. So then we can measure the received light. Next, we are going to measure the total amount of light output from the source or the luminous flux. So there are two methods, by using the luminous intensity and by using the illuminance. So if you want to use the luminous intensity, I, so you have to multiply I and omega, right? The luminous intensity and the solid angle. So then you can get the luminous flux. Or if you use luminance, E, so E into A, that is the luminous flux. So these are the two methods, by using luminous intensity and by using illuminance. So by using the luminous intensity method, this is called direct method, and the illuminance, this is called indirect method or substitution method. So by using the illuminance, we use Intriguating Sphere, and if we calculate the luminous flux using luminous intensity, then we use goniopotometer. Okay, so by using two instruments, we can get the luminous flux. So in the direct method, we do the calculation of luminous flux from luminous intensity by zonal lumen method and using distribution photometer or mirror goniopotometer. Then in indirect method, we do the measurement using substitution method using Intriguating Sphere. Okay, so we'll discuss one by one. So in the direct method, that is the using goniopotometer or distribution photometer, the input is I table or luminous intensity and the output is luminous flux. A good quality V lambda corrected photocell is required. Of course, we need the sensor. For direct method using Intriguating Sphere, we need the lumen output of a working standard lamp. Output is luminous flux. Again, a sensor is required here. This is a comparative measurement method. So, আচ্ছা এটা ভুল আছে, হ্যাঁ, এটা direct, এটা indirect. This is indirect method or substitution method. And this one is direct method. But first we will discuss the indirect method or using the Intriguating Sphere. Next we will go to the goniopotometer. So for Intriguating, have you seen this sphere at our lab? Anyone? দেখেছো কেউ?
মনে হয় দেখেছি।
হ্যাঁ মানে একবারই তো গেছো, তো জানি না দেখেছো কিনা। So as I told, this is used to measure luminous flux from light source by comparing with the flux coming out from any working standard lamp of known value. So the working principle is inter-reflected illuminance at any point on sphere wall is directly proportional to the lumen output from the source placed at the center of the sphere. So we'll see this one by one. This is the Intriguating Sphere. The lamp is at the center. We have to measure the lumen output inside. So this is the inside of the sphere. The lamp is placed at the center. These are the suspension wires. This is the luminaire, the lamp along with the luminaire, or you can just simply put the bare lamp. Then there is one auxiliary lamp here, a small lamp which is the part of the instrument itself. There is one baffle just to cover the auxiliary lamp. Then there is another baffle just before the photocell to cover the main lamp. The photocell, this is placed at the boundary. Just a minute. Okay, this figure is fine. So this is the sphere. It can be open and the place can be placed at the center. Now you can see the small hole here. So this small opening is there just to place the sensor. So the sensor will be placed towards the inside wall. Means the sensor will be placed inside the sphere and the meter will be somewhere here. So like as you can see, this one you can see, this is the opening here. So the sensor is placed inside wall of this integrating sphere, so it can be measured the lamp output. Otherwise the entire sphere will be covered, and then we can take the readings outside, because there is this wire is, you can see the wire. This is my sphere, this is the opening, the sensor will be placed towards this side, and then we have the meter here, so you can take the meter reading here. So what's inside the sphere? For that we have one main lamp. We will take the measurement for this main lamp. We have the luminaire here. Then we have the auxiliary lamp here, which is part of the instrument itself. Then we have used two baffle, okay, or just to separate the auxiliary lamp and the main lamp, and the main lamp and the photocell. So this is one baffle, this is another baffle. So validity of the use depends on the principle that illuminance received on one area of a sphere from another part is independent of the relative position of two parts. That means whatever light this photocell will receive, it is independent of the position of the emitter part. That means whether the photocell received the light from this part or from this part or from this part of the sphere, this all will be equal. We will see that now. And the luminance or the lamp to be tested is suspended at the center. The measurements are made by photocell, which is baffled, so that no light from the source can reach it directly. That means we have put this baffle in between the main lamp and the photocell. So the photocell will receive no direct light. See this part, there is the baffle. So it will be reflected. So no direct light will be received by the photocell from the lamp. It will receive only the reflected light from the different surface of the sphere. So this is baffled so that no light from the source can reach it directly. The inside of the sphere is coated with white paint of reflectance rho, which is assumed to behave as a uniform diffuser. So the inside wall of this sphere, you can see it's completely white. Barium sulfate একটা coating থাকে, which is very high reflective properties, so that the minimum amount is absorbed inside. The ideal part is that no light will be absorbed. It can receive total amount of light output from the source, but in practical, to make it zero is not possible. So the reflective properties of this inside paint is very high, so that the absorption can be reduced. Okay, and the outside wall is black, just to make the entire laboratory black. What is the outer color or outer paint, that is not the part of the measurement, but এটা যেহেতু ল্যাবে রাখা আছে, just to make the entire lab black, this is black painted. Okay, otherwise whatever be the color, that is not required here, but the inside color, it must be white. Okay, you can see L is the location of the lamp, and this delta S, this is the any surface, inside surface of the integrating sphere. P is the location of the receiver, and in this figure you can see this is L, the lamp. A is an auxiliary lamp, P is one baffle, Q is another baffle. Okay, and the C, this is the photocell. So the sensor is located here, it will do the measurement. Anyone, any question after this? আচ্ছা,
হ্যালো ম্যাম।
হ্যাঁ
ম্যাম বলছি ওই ইন্টিগ্রেটিং স্ফিয়ারের মধ্যে ওই অক্সিলারি ল্যাম্পটার ফাংশনটা কি, মানে ওটা কেন?
আসছি এরপর আসছি এরপর। আর কিছু কেউ? Okay, so let me explain at first. So let's consider a sphere of radius r, the sphere of the radius r with a light source L at its center. The inside sphere is coated with paint of reflectance rho. P is a point on the inner surface and it's shielded from the direct light by a baffle Q. So how much light will be received at point P? So this is L, my source. The sensor is located at point P. So what will be the light received at point P from any part of the sensor? Suppose this one. It will be I cos theta by d square, right? Like the baffle is here. So it will not receive any direct light from the lamp. Rather, it will receive reflected light from the different points of the surface, right? So we will consider any part of the surface, this part. So how much light will be received at point P from this delta S? It will be I cos theta by d square, right? What is I? Whatever the intensity in this direction from the S, then cos theta by d square. What is d? D is the distance between the source and the receiving point. So illuminance at point P, it will be delta I cos theta by d square. Now, then if you want to calculate the intensities, we know that luminance into area, right? Again, IP is In cos theta. If N is the intensity in the normal direction or the maximum intensity. So this is L into apparent area into cos theta. So now if you put this value of intensity, it will be illuminance into area, so intensity into cos theta by d square. Now this phi and theta, these are equal, so cos square theta by d square. This one. Now if you express d in terms of r, if you express d in terms of r, we will get 2r cos theta. So it will be L delta S by 4r square. So illuminance received at any point P or illuminance received at the sensor will be L. What is L? L is the luminance. Then this is the emitting area or that area from where the reflected light is coming by 4 into radius of the sphere. So you can see there is no theta, no phi. Means the S can be located anywhere of the inner surface of the sphere. That means it is independent of theta. So illuminance received at any point of the sphere from any point lying on the surface is independent of the position of the inner surface. Means if we want to calculate the light received at any point, it will be received equally from all the sides of the sphere. It is independent of the angle. ঠিক আছে? Okay. Any question? So that means no direct light will be received from the source, point 1, and point 2 is that entire amount will be reflected again and again, and it will be received by the sensor, irrespective of the position of the inner surface. ঠিক আছে? Okay, then the next point, amount of light. So the total luminous flux from the source, we know that if L is the initial luminance, A is the sphere wall, rho is the reflective properties of the inside wall. Okay, forget this. You just come to this point. This is another way of expression. Like F is the luminous flux, which is phi. এটা একটা বই থেকে নেওয়া, so এখানে F দিয়ে represent করা আছে, but this is my luminous flux phi, which is rho by A into phi. So this phi is the initial luminous flux coming out from the lamp. Okay, so then it will be reflected, and after first reflection, the amount of light will be rho into phi, right? If 100% যদি fall হয়, তো maybe 90% যদি আমি পাই, তো 90 into 90% of the total initial luminous flux. So this is after first reflection. After second reflection, this rho into phi will be again reflected. So again rho into phi. Then this is after third reflection. So as there is no absorption, so it will be continuing again and again. So then it will be rho into F by A into 1 by 1 minus rho. Okay. Now this is less than 1. And you can see this is constant for any particular sphere. This is constant for any particular sphere. A is constant for that sphere. So illuminance will be proportional to the luminous flux. So E is independent of the distribution of light from the source or luminaire. So theoretically, the reflectance of the surface is known. So we can calculate F by measuring E. So these are the two properties. The first one is that the received light from any surface of the sphere will be constant irrespective of the angle. The second one is that the illuminance will be proportional to the luminous flux of the light source. Okay. So these are the two basic properties behind the measurement using the intrigating sphere. But how do you do the measurement in actual cases? How do you do the measurement in our lab? That is using the substitution method. এত কিছু করা হয় না, rather we use this substitution method. What is the substitution method? We have two lamps. One is test lamp, যার output আমরা measure করব. Another is standard lamp. We already know the output of the standard lamp. So phi t we have to find out from the experiment. Phi s we already know. So just place the phi t inside the sphere. Take the reading outside. What will be the illuminance received at the Lux Meter Sensor? That is ET. First part is completed. Next, you put the standard lamp inside the lamp. Take the reading. It will be ES. Okay. Now, as E is proportional to phi, so of course phi t by phi s will be ET by ES. So this is the expression of phi t. Phi s is already known to us. ET we have measured. ES we have measured. So from here we can compute phi t. Okay. So this is called the method of substitution. Like if you want to measure the light output of a filament lamp, so you put the filament lamp inside the sphere, take the reading in the lux meter, that is ET. Then you put the standard tungsten filament lamp inside the lamp. You take the reading, that is ES. So phi t will be phi s into ET by ES. So from here we can calculate what will be the total lumen output of phi t. Okay, but this is only applicable when the dimension of the test and the standard lamps are same. Why dimensions need to be same? Because if the dimensions are different, if the dimension of this L and suppose a small L is here, if these are different, then you can understand that the absorption of light, reflection of light, this will be different. If the test lamp is much bigger than the standard lamp, or the test lamp is much smaller than the standard lamp, the amount of absorption by the surface of the lamp will be different, right? So there will be small amount of error due to this dimension mismatch of the test lamp and the standard lamp. So just to compensate that error, we need this auxiliary lamp. You got my point, na? That the dimension of the test and the standard lamp must be same, just to avoid the error from the absorption and the reflection by the lamp surface itself. So if we want to compensate that error, then we have to consider the auxiliary lamp. So the auxiliary lamp is used to compensate for absorption of inter-reflected light when the dimension of test lamp and working standard lamps are different. So then this will be the expression phi t by phi s equal to ET by ES into ES by ET. Instead of this simple one, now we have this error correction factor, ES by ET. So what is the small ES by ET? So at first my test lamp is inside the sphere. Therefore this is the test lamp. The auxiliary lamp is off. You take the reading, that is capital ET. Then the lamp is inside. Just switch on the auxiliary lamp. Then we can take the reading here. That is small ET. Then the next step, replace this test lamp using the standard lamp. Take the reading, it will be capital ES. Then switch off the standard lamp and switch on the auxiliary lamp. We will get small ES. So there will be a small difference between this small ES and small ET. মানে টেস্ট ল্যাম্প আর স্ট্যান্ডার্ড ল্যাম্পের ডাইমেনশন যেহেতু ডিফারেন্ট, সো অক্সিলিয়ারি ল্যাম্পটা শুধু অন করে আমি কতটা ডিফারেন্স পাচ্ছি বিটুইন ইএস অ্যান্ড ইটি, দ্যাট ইজ দ্য কারেকশন ফ্যাক্টর. So thus we can get the difference due to the dimension mismatch of the test lamp and the working standard lamp. ঠিক আছে, or any question? বোঝা গেছে কে জিজ্ঞেস করছিল অক্সিলিয়ারি ল্যাম্প?
ইয়েস ম্যাম।
Okay, so if you purchase one 18 watt CFL from any market, you want to find the total light output of that CFL bulb. So what you have to do, you place the CFL bulb here, you take the reading, then you put one standard lamp inside the sphere, you take the reading. যদি দুটো dimension match হয়, then no need to switch on the auxiliary lamp at all. Or যদি আমার সেম স্ট্যান্ডার্ড ল্যাম্প না থাকে, যদি আমাকে অন্য কিছু স্ট্যান্ডার্ড ল্যাম্প নিতে হয়, then you have to do that extra part using the auxiliary lamp, right? Just do the correction. Okay. Okay, so here we are the absolute measurement or the main measurement which we do using the Intriguating Sphere is the lumen output. Then instead of that, we can also do the measurement light output ratio and ballast lumen factor. If you remember the light output ratio, that was the efficiency of a luminaire. How much light we can get if we use the bare lamp along with a luminaire. Instead of the street light, always we using the luminaire. So how much light we are getting from the luminaire instead of the bare lamp. So luminaire output ratio is the luminaire lumen to the bare lamp lumen. If there are more than one lamp, then total lamp lumen. Then the ballast lumen factor. What is ballast lumen factor? This is again the efficiency of a ballast. Ballast you can see along with the tube light, right? Later we have this why we need to ballast, what is the function of ballast, etc. But all of you have seen the ballast at your house with the fluorescent lamp, right? সবাই দেখেছো না বাড়িতে টিউব লাইটের সাথে থাকে?
হ্যাঁ।
So what is this ballast lumen factor? That is the efficiency of the ballast. Output is the lamp lumen with the test ballast. How much light we are getting from any lamp if we use that particular ballast, to the ratio আমি কতটা lamp lumen পাবো if you use the reference ballast. So this is the ratio of the luminous flux using that particular ballast to the luminous flux using the reference ballast. So how can you compute the light output ratio? Just do the measurement along with the luminaire, take the ET, and for the second step, do the measurement with the bare lamp. You take the reading ES. Right? So here we don't have to use the standard lamp. Right? So you use the measurement using luminaire, you do the measurement using lamp lumen, just take the ratio, you will get the light output ratio. So just place the luminaire inside the sphere. The lamp is on inside the luminaire. Auxiliary is off. The reading is A. Then the luminaire, ebar ki luminaire dimension and the lamp dimension, of course, those are different. So now we have to use the auxiliary lamp. So in the second step, the luminaire is inside the sphere, but it's off. Auxiliary ta on kore, the reading is P. Then we will place the lamp instead of the luminaire. The bare lamp is off, auxiliary on, that reading is C. And if you make the auxiliary off, the bare lamp on, the reading is D. So it will be first key chilo ET by ES, right? So luminaire reading, which is A, lamp reading, which is D. So A by D, and then the auxiliary reading. So that's our B and C. So C by B. Okay. And for ballast lumen factor, you do the measurement with test ballast, do the measurement with reference ballast. Just find the ratio, we will get the ballast lumen factor. Any question? বোঝা গেছে? Any question, anyone? কি কার কোনো কোশ্চেন নেই? Yes or no?
It's okay.
So in this figure, so this is the inside sphere. This is the suspension wire. This is my main lamp placed over here, and you can see a small light here, right? This baffle is placed just to cover the direct light from the auxiliary lamp. So at first we have to switch on the main lamp or main luminaire, whatever. Then you can take the reading using this small light. Okay, this is a small auxiliary lamp over here. The dimension of the auxiliary lamp is very this one. This is the main lamp. This is one baffle. This is the auxiliary lamp, another baffle. Here we have the sensor, then this wire, and we have the lux meter or whatever meter outside the sphere. Okay, so any question? RQ? Hello? আর কিছু কোশ্চেন? বাকিরা কেউ কিছু রেসপন্ড করবে না? 39 জন আছে না, 39 জন। কারো কিছু কোশ্চেন নেই? Okay, so can I close now?
Yes, ma'am.
আচ্ছা, ঠিক আছে। So our next class is on Friday, তাই তো?